Hi, this video is about searching, and it's not about searching linearly, but it's about something called binary search, where we can actually utilize that we know something about what we're searching. My last video was about the linear search, where we're just searching things one at a time, and we made this small program here. I made this small program here where we could find the index of an integer in an int array. So we randomize the list and we find the number. So what if we know something about this list here? Let's just create a new document here. So let's say that we have something like these circles here. Like we have like these guys here. Let's say that they're not really like this, but they are more like this. So you probably see now that there's a difference that in this list here, these are sorted by size. So the smallest one is to the left and the biggest one is to the right. And let's also say that we're looking for one of them. Let's say we're looking for the red one. So in the normal linear search, what we would do is we would look at the first element, then second, third, so forth. So we would be looking 1, 2, 3, 4, 5, 6, 7, 8 times until we find that one. So in the linear version, we would be looking 8 times to find that specific one here. So because we have 8 circles here, when we do what we would call binary search, we try to divide it with the knowledge that we have. And in this case, we know that they are sorted by size. So what we do with binary search is we kind of say, okay, let's find the middle. So I find the middle here. Let's call this M. And we have the start over here, and we have the end over here. So what we do, we kind of take the middle. We cannot take in between two, so we have to choose, do we take the one to the right or the one to the left? Let's try to take the one to the right. So in this case, we are looking for this big circle here. So we're going to compare, let me draw that. We're going to compare this, the one we're looking for. Remember, we haven't found it yet. We're looking for that, and we can see that we are a lot bigger than the one we're looking for. Because we know that everything in this area will then be smaller than this one. So we are certain that the big one is going to be over here. So we can remove this entire part of it. So in the binary search, we go from having 8 things we have to go through linearly to only have 4 things. But there's no reason to stop now. Now we have a new list here where we have a start. We have to move the start to here. We still have the same end, and we create a new middle here. So the new middle, then again, we're going to compare the circle we're looking for to the one to the right of this. And the one to the right of this is once again smaller, so we can now also disregard this part of the list and only look at this part of the list. So now again, we move the middle here, and we move the starting point here, and we look to the right and we see we found what we're looking for. So the second comparison was between here, and the last one was itself. So it did one comparison with this one comparison with this one, and one comparison with this one. So with the binary search, we actually only needed to do 3 comparisons. And with the linear search, because it was the last one, we had to do 8. Of course, if it was the second one, we probably would win with the linear search. But as these lists of items grows larger, the benefit becomes increasingly larger. So let me show you. So let's say that we instead have a very large list of numbers. Let's say that we have 1 million numbers that we are looking through. Let me just... So if we're going for linear search, we could be unlucky and the last one is the one we are searching for. Then we would have to look through all 1 million. If it's the first one, we could get very lucky, of course, and it would be the first one we are looking at. So it's kind of hard to say, but we would most definitely at least have to go through half of them or more. So it's a very, very big task to go through all of these items. But if we are instead using this binary search, what we can look at is that the first lookup we're going to do, let's say, first, let me draw something. Let's say we have all the items in this box here, and they are all sorted. So in the first breakthrough, or the first search, we can actually cut half of them out of the equation because we know it's not going to be in this part. So when we're in after the first comparison, we have 500,000 left to search. So after that, once again, because we're using the binary search, we can actually go in and say, okay, let's just consider only half of that. So now in the second run through, for the binary search, we have only 250,000 that we need to go through. And again, what we can do, because this is binary search, once again, we can compare the sizes or however this is quantified. So this was disregarded, this was disregarded, and now we only have to look at these items and so forth. So this way, we are always halving whatever area we need to search. And at some point, we come to a point where there's only one item left. And this is going to be really fast. So if we take number 3, for example, that would be 125,000, and number 4 would be something like, let me just say 60,000. I know it's not completely 60, but it's close. And then on number 5, it would be 30,000. Number 6 would be 15,000. And we're going to continue until we find it. And number 7, lucky number 7, it is then 75,000. And again, we're going to cheat a bit. Number 8, it's around, let's just say 35,000. And number 9, it's somewhere around 17,000. And we go for 10. And we around 8,000. Again, I'm rounding a bit here. And around 4,000. And 12, we are around 2,000. And 13, we're around 1,000. And let's continue. And 14, we are around 500. And 15, we're around 250. 16, 125. 17, we're just around 60. Again, I'm just rounding a bit, and then we're on 30, and then we're on 15, and then we're on around 7, and lastly 21, we're around 3, and 22, we have 1 or maybe 2 left, so it's around 22 searches for the million. So by halving each and every time, we will find it after only 22 lookups because we know they are sorted. So whenever we have something that's sorted, we can use other methods than just linear search, which is very, very powerful for us. So the difference between 1 million and using binary search is around 22 searches for this one and 1 million for this one. And the worst case scenario is that, let's say we're looking for something that isn't really here in the box, then we would still have to search through all of them to know it's not there. But in the binary method, we only need to search through 22 because we know if it's not here, we know that it must be, it should be there. So we know that it can't be in this pool of things that we have here. So yeah, so this is basically how binary search works. We take something, we divide it into halves. Let me just show you another example of binary search. So I have a gun. Let's just draw that for a second. And let's draw it in green. So I have a garden that looks somewhat, oh, I wanted to use this, somewhat like this. And yeah, and let's just fill out everything here. Oh, that didn't work. Okay, so this is my garden, and what I also do have is I have a small lawnmower that sits over here that mows my garden, so I don't have to do it myself. And for that to work, there's actually a wire going on the inside here of my entire garden so that it can actually know when to stop so that it doesn't do anything bad or something like that. And my house is here. Okay. So when my lawnmower drives around here, it needs that this one to be connected in plus and minus here. If it's not connected, then the lawnmower won't work. It can feel a magnetic field and it needs to be in a circle here for that to work. So if I cut this anywhere, I have a problem because then there's no circuit and my lawnmower wouldn't run. So at one time I had the problem, I was trying to trim the sides of my lawn and accidentally I had cut the line somewhere, but I had no idea where I had cut the line. So what I could do is I could take a shovel and then start shoveling and digging up this wire that is buried into the grass. I could dig up my entire grass lawn here and then try to find the wire and see whenever I would find the point where it was broken. So let's say it's broken. Actually, when I tried it, it was actually broken right here. So what I would have to do then, either I would dig it up from this side or I would have to dig it up from this side in order to figure out where it was actually broken. That would be a simple linear search. And if I started on this side and it was broken right here, it would take me a long time to find it. And opposite, if I started here and it was broken right here, it wouldn't take very long. But it was actually broken over here. I had accidentally cut the line right here. But I can't see it because it's buried underground. So I needed to find that. So one cool thing I figured out is I could use binary search here. So what I would do is I would just take off the plus wire here, just move it to the side like that. And then I would take a new wire, put it on the plus side, and put it on roughly the middle of this. When I did that, I could see on the light in here if there was a connection or not. What I immediately realized by doing this is that yes, there was actually a connection, so I know that this entire line is not broken anywhere. So then I did the next thing. I tried to connect the wire to the second part where I thought is halfway between, so it's approximately here. So I did like this. Of course, I removed the other one. And now I could see that there was a problem because now there's no connection because it's broken here. So now I actually realized that at some point here, I had a broken connection. So what I did again, I removed this one and I tried to find the middle again, which was approximately here, I think. So now it worked again. So now I know that my disconnected part is around here. So the next thing I did, I put a new wire from the middle here. And now I know the disconnected part is around here. And then I talked to my wife and I actually found out that this was actually the problem because of something with some, pathway or something like that. So that means that this way I could find it much, much faster than if I had used my good old sequential search. And again, this is not like in the situation with the objects that are sorted, but it's because I know that the line must be continuous all the way through. I could use binary search on this as well. So you could probably imagine there's a lot of situations where you kind of have to utilize the knowledge you already have about the situation to figure out a way to use binary search. Okay, so that was kind of like the entrance to that. So let me show you an example in Java. So in Java, what we are going to try here is we're going to sort some arrays. So let me just draw some array here. Just real quick. I'm not the best with this paint thing. So I have this array here, and then I have like index number 0, index 1, index 2, index 3, index 4, index 5, index 6, and index number 7. So all in all, I have 8 indexes here. And within this, I have different numbers. For example, lucky number 7, number 8, number 10, number 15, 31, 35, 60, and 99. So now we have these numbers, and these are sorted from smallest to biggest. So when we're doing this algorithm, the first thing we're going to do is we're going to define a start and an end. So we're going to define the start here. The first element, or index 0, is going to be the start. So we're going to say that index 0 is the start. And we are also going to say that index number 7 is the end. And the next thing we're going to do, we're going to find the middle. So because this is an 8 element, the middle is right between these two numbers. So we'll just choose it to be bigger than or smaller than. If it is if we just go bigger, let's say we need to find number 60. Then I look here and I see that 15 is smaller than 60. So I need to remove this part of the array. So in order to do that, I'm not really going to delete it because that's going to take up a lot of time. I'm just going to move the start over here. So the middle, so the middle actually becomes the start. And now we are back in business. So again, we find the middle here. and right again, it's right between. So we look at the element to the left, which is 35, which is smaller. So once again, we can remove this part of the list and look into this list, and we remove the starting point again. And we put the starting point where we had our, so we put starting point here. And now the beginning and the end are right beside each other. So now we have two numbers, we look to the left and we actually find the one we're looking for. So what we need to do, we need to define a start and an end, and we need to calculate the middle all the time in order to know which way we need to go, what we need to disregard and stuff like this. So let's do that. So in my previous example, what we've seen is that I only have like random numbers like this, and they're not sorted. We cannot use binary search on an unsorted list because we cannot utilize any information because we don't know anything about the numbers that we can use for the binary search. But if they are sorted, we can actually utilize that. So right now it's finding number 3 at index number 6. So let's just try to sort them. Fortunately, in Java, we have something called arrays .sort, which will sort any array. Default sort will be from smallest number to biggest number. So if I do it again now, I will first create the list, sort the numbers, and it will look like this. And we can see that 3 is at index 0 now. So we can also look, let's look for the number 94, and it will be at index number 29. So we also know that it needs to check through 30 different indexes to find the 94, because the first one is 0, so it needs to go through all of them to find it. Okay, so let's try to then implement binary search to see if we can actually do this a little better. So what I'm going to do is, so this is actually just a normal search. So I'm going to do the other search as well. So sort, I'm going to say binary search found, and then again I'll do item. We'll look for the same item at index, and then we would say binary search, and then we need the number that we're searching for, so that is called item. And of course I don't have this right now, so what I'll do, I'll just create it in here. So that's it. So it says it's going to return a string. I don't want that. I want to just return the index of that, and that will still work because Java will automatically change this into a string up here. So yeah. So the next thing we need to do is we need to define this binary method here. So the first thing I showed you in here is we need a start and an end, and it needs to be at index 0 and index 7. And in this case, we don't know if it's 0 or 7 because we don't know the length of the list, so we have to use that instead. But we do know that the starting point is going to be 0 because the integer arrays in general in Java always starts at 0. We want the end to be at the end of the list. And we know the list we're working on is numbers, so we can use numbers.length. The problem is that if we use numbers length, we know the length was 8. So that would be outside of the index. So we have to subtract 1 to get the last index of the list. So I'm going to do that by saying length minus 1. so that we are not going to have any problems with going outside of the list. So how do we find the middle? So let's define middle as being equal to something like the last index divided by 2. But the problem is that we can't always do that because sometimes we move the start. So if we just take the last index here, this will be the middle. But if we move start up here, then the middle would be here. So we need to calculate in the starting point as well. So if I take the end minus the starting point, I get this length here. So let's say the start is here and the end is here. So that would be 7 minus 4, which would be equal to 3. So then we know that 1, 2, 3, this would be the middle. The problem is then 3 is really this one here because we haven't taken into consideration the starting point. So we also need to add the starting point, which in this case was 7. So the starting point would be, 4. So the starting point would then be 4 plus the 3. So we would, yeah, we need to add the starting point as well. So, and then subtract that from the last element, that would give us the middle. So let me show you that. So we'd say, instead of using the end like this, we would say we want the starting point plus the end point minus the start point divided by 2. So if we look back here, so that would be the starting point. Let's say that we cannot be between these two really. So let's say that this is the starting point S here. So that means that the starting point would be 4, and we add that to the end point, which is 7, minus the starting point, which was 4, divided by 2. So 7 minus 4 divided 7 minus 4 is the same as 3 divided by 2, and 4 plus this. So because this is integer division, so 3 divided by 2 is the same as 1, so we would get 5, so this would be our new middle. So this is why this works. So the next thing, now we found the middle, we have to look at the middle and see if that is really the number we're looking for. Because we could get really lucky that if we were, for example, looking for 31, we have to look and see if that's really the one we are looking at. So we're going to say that if the middle index happened to be the same as the item we're looking for, then we just immediately return the middle index. Because then we don't need to do anything else. We found what we're looking for. Unfortunately, we are not that lucky always. So there's also another situation. So if, let's just copy this part. If the number we're looking for in the middle is actually smaller than the item we're looking for, then we need to move the start, because that means that we need to move the start because we're looking here. If we're looking for some number here and it's smaller, then we need to go and disregard this part, so we move the start. So we're going to say that if the number in the middle is less than what we're looking for, we're going to say that start is then equal to the middle plus 1, because there's no reason to look at the same element once again. Remember, we're going to look for the middle here. And then the next time we go in here, so we have to say +1 because we want to disregard the item we already looked at. The only other real situation that we can have is if numbers of the middle is actually bigger than the item we're looking for. Then we would know that we need to move the end instead of moving the start. So we move the end to the middle, and this time the other way, -1. So if the element that we're looking for, let's say that we are looking for an item that is smaller, let's say we're looking for 8, we go in here, it's element number 31, so we know it's smaller, then we move this end here to not to 31, but we move it to 15 because we don't need to regard that part of it. So that's it. So now we can actually find a new middle, but the problem is that we also need to do this more than once. So we actually have to do this part here. We have to do that until the start and the end comes together. So in the event that we don't find what we're looking for, or it's the very last item, we see here start and end is going to get closer and eventually be the same thing. If they go completely close and is the same thing, then we know we have no more to look for and then we haven't found it. So we can make this into a small loop where we're going to say while start is smaller than or actually also equal to the end. Then we're going to do this. I'm going to start here and we're going to end right after this one. So this loop is going to run until start is no longer equal to the end point. And then we're going to say return -1 outside. So if we go through all of this here and we don't find anything, then we will just return that we didn't find it, and we signal that by -1 because what we're putting back is an index, and an index can never be -1. So we know if we get -1, we didn't find it. So let's try and see if that works. I should be lucky if all of this coding just works without any hassle. And it actually found index 94 at here, and also binary search found it in the same place. So let's do the ends of it. So let's go for number 3. That's in the other end. And that also worked. Let's go for a number that's not there, number 2, and see if we go into an endless loop. So only binary search didn't find it. Okay, and that's because the normal search doesn't say if it doesn't actually find it. So it just skips it. So it actually works for both of them. It can skip numbers it cannot find and so forth. So it might be interesting to count how many lookups we're actually doing. So let's try to do that. So in order to do that, we need to know how many times are we actually looping through these things here. So I think I'm just going to refactor it a bit and put also the non-binary search out here. So I'm going to say int linear search. And again, we're looking for a specific item. And then I'm going to take the loop here and move it in here and copy this one up here and then say linear search found item, and then let's not do the linear search, let's do the, or binary search, let's do linear search here. And of course the item, we need to specify that it's an integer like that. Okay, And instead of doing this part, we will then, just return I. And if we don't find it, we better return -1. Now these two are working, these two are working in the same way. So now when we're looking for 2, we should see that we actually have -1 for both of them. And let's just check to be certain that we can find something like 30, because that's also there. And both of them should find it, no problem. Okay, so let's count them. So let's see how many loops are we actually going through. So let's put a couple of counters up here. So private static int lcount equals 0 and private static int bcount equals 0 as well. And then whenever we're going through the loop here, we're going to say lcount plus plus, and whenever we're going through the loop down here, let's do this. Oh, we better do that just before here, so we'll say bcount plus plus here as well. So now we know how many times we're going in here and going around, and how many times we're going in here and going around. So yeah. Okay, so now we're counting it. So let's print out like this. We're going to say linear comparisons. And then we're going to say lcount. And we're going to do the same for the binary so that we can see binary comparisons as well. And of course, we need to change this into bcount. So now we're counting one and the other. Let's see what it says. And we can see that the linear comparison for the number 30 would be 13. So that corresponds to the index because it's the index plus 1 for linear searches, and binary searches needed 4. So it's a lot different. There's a big difference there, right? And let's look for one in the ends, like 94. Let's see. So that would be 30, and that would be 5. Okay, so when they're this small, let's go bigger. So let's make 1,000 elements in here, and let's see what the difference is. So now we see that, oh, the numbers are quite small. But now we see that it actually finds it at the first time it finds 94 is at index 930 because they are sorted and there are only 100 numbers but 1,000, so they would be like 10 times each. So it's kind of a bad example. So let's also make the random numbers dependent on the amount in the list. So let's say instead of saying the next int should be 100, let's put it into the random numbers to be numbers length multiplied by 10. That would give us a much more broad range of numbers like that. And none of them actually found number 94 in this case, and we can see it had to go through all thousands in the linear comparisons, and it only needed to have 10. So the cool thing I want to show you now is that now it needs 1,000, and when I double this number, I doubled it. Now it needs this, the comparisons also double here, but here they will only increment by 1. And this way, if we keep doubling this, this will only increment by 1, but this will actually double. And that's because this is linear and this is logarithmic. So for a very large amount of numbers, it will be very efficient. So let's try with 1 million numbers and see if our calculation from before at around 22 would be sufficient. Of course, it needs to print out all the numbers first. So it needed only 20 in this case to find oh, it didn't find 94, so it's quite the coincidence, but it needed actually only around 20. Maybe some of my calculations weren't that correct, so it needed only 20 comparisons in order to find out that it was not in the list. And of course, this is only doable because this is a sorted list and not an unsorted list. And if we don't print it to the screen, we can actually see that both of them are working very, very fast. It seems like they're all going slow, but if I remove this print numbers, we see that it actually goes really fast. There's no delay at all. So we could also time it, but I know from experience that even 1 million elements in linear searching is no problem here. But in some cases, it could be. Okay, so that was it about binary search. You can find this algorithm everywhere if you want to, or you can try to implement your own. But that's it for now. Bye.